on to the lecture slide. Okay, continue, which we will continue after on to the nomenclature. First, as I have promised, we will learn on how to draw the structure, okay, based on this projection. So you have a few type of projection, okay, which I've shared in the slide. Okay, the first, which is the wedge dash, okay, and then we have also the Newman projection, and we also have sawhorse, and the last one would be Fisher. Okay, the last one would be the Fisher projection. So for today, I will cover these three first on how to draw them. Okay, so these projection are used at a different time. Okay, for example, like when for wedge dash, this is mainly used when you only have one chiral center. Okay, meaning one chiral carbon that is available in the compound. While for Newman, okay, Newman and also Sawhorse, these two, okay, it is best to use when there are two chiral centers. Okay, when there are two chiral centers available in the compound. While for Fisher, this one, when you have two or more. Okay, sorry, not this way. It should be more or equal than 2, then you can opt for Fisher projection. So for the wedge dash, we're going to look for this first. Okay, number 1, wedge dash projection. So this is mainly used for compound, organic compound with one chiral center. So recap, a chiral center or a chiral carbon, when you have this carbon in the middle, is bonded to 4 different atoms or group of atoms. Okay, you have A, B, C, and D. All of this is different. Let's say, for example, okay, you can have carbon in the middle with on this side you have hydrogen, okay, and then you have chlorine. You might also have an ethyl group, CH2, CH3, and on this side, there could be a hydroxy group. So this carbon, which is here, is considered to be as the chiral carbon or chiral center. So this carbon is bonded to 4 different atoms. Okay, atoms as in just hydrogen or chlorine, or group of atoms. Group of atoms, example is like OH or CH2, CH3. Okay, so it can be atom like this, just one element, or it can be group of atoms. So based on this, you have determined that there is a chiral center, for example, in a compound. So that can be drawn uh, differently than the usual way, which is this is like 2D representation, just flat on a piece of paper without knowing the how to say, the geometrical shape of it, okay, how it is arranged in space. So that's why we use all of this type of projection. So for wedge dash projection, so what you normally do is you always start with the carbon in the middle, okay, which is the chiral center or the chiral carbon. So always start with the uh, chiral, okay, chiral center C. And then what you have to do is to draw one line, okay, just one line like the normal bond that you draw, okay, from this structure, okay. And then another one could be to this side, okay, or it could be here. So just 2 of these using stick lines. Okay, then we have these 2 wedge, okay, wedge shape, okay, like last week Matan asked, okay, there's one with dotted dash and another one with bowl. So actually, okay, the one with bowl will be something like this. Okay, so the one with bold dash is the direction is pointing towards you, meaning towards you is towards the viewer, which is us. So this is from our angle, our eye angle. This is how we view the compound. So whatever atom that is situated here, let's say I put here A, okay, and then B and C, for example. So atom A or group of atom A is actually sticking out and pointing towards you. But the carbon still maintain its tetrahedral shape, okay, but then it is pointing towards you, okay. Then we also have another uh, bond, okay. It must have 4 bond. So that one also will require a wedge bond, what do you call that, bond shape like this. But then that bond is pointing away from you, which is to the back. Okay, this one, the bowl is pointing to the front, in front, coming out, pointing towards you. But what we have at the back will be drawn, okay, still in wedge shape, something like this. So this is pointing towards the back, okay, away from the viewer, away from you. Okay, so we can place this as maybe group D. So this is just how you draw the wedge dash. Okay, it is the same even if you draw it the opposite direction. Okay, let's say you don't want to draw it on the right side. Okay, you can draw carbon in the middle. Always start with the uh, stick line first. Okay, then you can start with the bowl. Okay, bowl wedge and the dotted wedge. Okay, so this is how um, it is being drawn. Okay, and you have you tried to use the software that I have suggested? Dah cuba tak? If you have tried, okay, then you have the experience of actually moving this whole compound. Okay, you can move the whole structure around and see uh, and try to position it so that it looks like this. Okay, in which that, let's say I draw this same structure, okay, and you want to have probably the H on top, and then you can have the CH2, CH3, and you can have your OH here and your chlorine. Okay, so this structure can be drawn this way. Okay, it can be drawn from the 2D, okay, and be converted into something like 3D structure. Okay, this is for one chiral center. Okay, it can be used when it is having only one chiral center. And normally, if you were asked to um, identify the chiral center, we will use the asterisk symbol on the carbon atom. Okay, on the carbon that is chiral center. Okay, any question for the wedge dash? Ada soalan? All is clear?
So,
Yes?
what if kalau satu daripada cabang tu dia tak ada group? Maksudnya dia macam ada satu cabang je tapi dia tak ada tulis apa-apa macam methyl group ke OH group ke. Dia
Mm-hmm.
considered methyl lah.
Macam mana? Macam mana?
Macam contoh the dotted one tu kan
Okay.
adanya Cl kan. Tapi kalau
Okay.
Cl tu dia tak tunjuk. Maknanya macam remove the Cl. Kalau dia tunjuk wedge je.
Oh, tak
That
boleh.
group.
Kalau you pakai structure wedge dash, you must always show the group ataupun atom yang berada kat situ. You must always show. Dia tak boleh macam skeletal kan. If you skeletal, you just draw something like this and then draw macam ni kan. But if you draw it like this, macam ni, it is normally you have to actually show the what do you call that, the structure. But in skeletal form that will be different. Yang tu nanti kita akan tengok. Kalau skeletal, yes, sometimes you will see that it will be something like this, and then you will see. But then again, normally even if there is hydrogen, they will show hydrogen. Okay, even if it is CH3
What if
group,
hydrogen?
if yes,
Kalau macam tu kalau dia jadi macam tu so dia nak
kalau
automatic jadi metil
uh, uh, if it is like this, then you can consider it to be methyl group. But then it is best practice to always show. Even in question also, kalau you jumpa macam ni, dia akan tunjuk group of atoms atau atom yang berada dekat situ. Otherwise, kita tak pakai macam ni lah, just tunjuk macam ni je. So that is the purpose of having I have to say stereochem structure, something like this. Okay, Aisyah?
sebab
Alright.
saya ada nampak ada satu
Example.
diagram tu dia
Dia
macam
tak ada kan?
dia tak ada tulis macam dia nak consider H ke atau metil sebab nak dia
Kalau
chiral tu kan.
yes, correct. Kalau tak ada, then normally it will be considered as a carbon lah at the end. But kalau hydrogen ada pun, you must be, kita kena tunjuk kat situ kena ada hydrogen. Okay. So, ada lagi soalan? Any question before I go to the Newman projection? Tak ada? Okay. So, on the second one, okay, the second one, which is the Newman projection. Okay, so this is when you can have the rotation, okay, upon this CC bond, okay, but the structure, okay, basically, if you look on the structure, suddenly you see that you have a round shape and then something sticking out like this, right? So what you see over here is basically the carbon. Okay, you are viewing the carbon from the angle. Okay, the front angle. Okay, the front meaning from this angle. Okay, directly on the carbon. So what you have to do in order to draw the structure, let's say you have a 2D, okay, between these two carbon. Okay, always focus on the CC bond that is in the middle. Then let's say, okay, you have this one a CH3 group. This could be hydrogen and another Br. And on this side, okay, you can have methyl, for example, a chlorine, and another hydrogen. So how are we going to convert this structure into this Newman? So you have these two carbon that is in the middle. So these two carbon is the chiral center. Okay, because all this carbon is bonded to 4 different atoms or group of atoms. So once you have this, you have determined the chiral center, then you can start to draw the Newman projection. So what you have here is my advice is to draw the circle first. Okay, the circle doesn't look like a circle. Okay, a circle in the middle. Okay, once you draw the circle, you draw the carbon that is in front. Okay, the carbon that is in front. Okay, you see that there's only 3. Okay, why only 3? Since this carbon has 4 bond, because the CC bond, which is this one, is not actually shown because we are viewing it directly from here. Okay, we are viewing it directly from this side. Okay, it's like your eyes is here. So this is the front carbon. Okay, and then you can draw all the what you call groups, okay, atoms or group of atoms that is attached to it. So you have chlorine, then you have your CH2, CH3, and you could have your hydrogen over here. Okay, so this is the front carbon, and then the one at the back, use different color. Uh, okay, the one at the back over here, the back carbon. So for this uh, carbon, okay, the C is not shown. Okay, what you will see is only the atoms and group of atoms, which is the Br, hydrogen, and CH3. And this depends on whether it is staggered or in eclipse position. If it is staggered, then it will be the opposite, which means that you have to draw the back uh, atom or group of atoms this way. Okay, so it is like not overlapping. So this would mean you have CH3 over here, and you can have hydrogen and bromine. Okay, so this would be the staggered conformation. Then, if let's say you have the same structure, but now you want to rotate, okay, you rotate at the CC angle, which is you rotate by 60 degrees. Okay, 60 degrees. So then, same step, draw the circle, draw the groups that is in front. Okay, so the front will be the same, CH2, CH3, and then chlorine. Then, when you want to draw the atoms that is attached to the back carbon, okay, so now it is in eclipse. Eclipse is like it is overlapping, but truly, if you want to draw it like truly overlap, then you cannot see lah. Okay, tak boleh nampak kan. But to draw it, you have to draw the line slightly shorter. Okay, slightly shorter. So it's like showing it is at the back. Okay, the front has the length is uh, how to say longer because it is in front. So the length at the back, okay, it is shorter to show that it is further away. Okay, further away from our eyes, so it looks short. Okay, then once you draw this, you draw all for the three bonds. So one, two, and also three over here. So then you can have your BR. So from here, it is like it is rotate. Okay, it rotate, rotate, rotate. So BR will go to this side. This would be your hydrogen, and this would be your CH2, CH3. Okay, so and this would be your eclipse conformation. Okay, eclipse conformation. Okay, so any question on this one? The Newman? The soalan? So basically, you just have to draw the circle, okay, and then the atoms or group of atoms that is attached to it. Okay, the one in front will always be, you can make it at the same position. Okay, you just rotate the carbon at the back, okay, and whatever atoms that is attached to it. So that would be for Newman. Okay, then the third one. So the third one would be the Sawhorse projection. So for Sawhorse projection, I will use the same example, which is CCH, BR, CH3, and then CH2, CH3, chlorine, and hydrogen. So with this same structure, we will convert it into a sawhorse, okay, into a sawhorse projection. So in sawhorse projection, the first step is to draw a line, but the line must be at a slight angle like this. Okay, draw a line at an angle, and then same like in the Newman projection, this would be considered as the front carbon. Okay, front carbon, and this would be considered as the back carbon. Okay, you have your front carbon and your back carbon. So once you have this line, you can draw the atoms that is attached to it, or group of atoms. So okay, so we start with the front carbon. So you have sorry, okay, then you draw a straight line like this. So this is to show a bond which is the same like this hydrogen, okay, which is straight. Then you have sort of like a lake. So that's why this is called the sawhorse projection. Okay, you have a lake. Then at the back, also the same. You have some a bond sticking up and another two leg. Okay, another two leg. But this would be the eclipse. Okay, eclipse conformation, which is the same as this one. Okay, so and then once you have this structure, you can put all of the atoms and group of atoms. So H, CH2, CH3, chlorine, and then at the back you can have your bromine, hydrogen, and CH3. Now, if you want to rotate, okay, rotate at this CC bond, 60 degrees. So draw the same line. Okay, the front carbon can be at the same position like this. And then you have your hydrogen, your chlorine, your CH2, CH3. But the back carbon now will be different. So this will go here. Okay, this one will go here. This one will go on top. So what you have is now the leg is at the top. Okay, and the straight line is pointing downwards. So it looks like a Y shape. Okay, it looks like a Y shape. So this would be your staggered. Okay, staggered conformation. So this would be your Br, because the Br is now going down, and you have your hydrogen here, and this is your CH3. So this is how you draw the sawhorse projection. Okay. So any question?
Sir,
Yes.
yang apa rotation tu kan?
Hmm?
Kena lukis juga ke?
Oh, tak perlu.
Tak payah.
Saya just tunjuk je. Okay, tak, yang arrow ni tak perlu tunjuk. Okay, clear? So these three, okay, earlier we have the wedge dash. Okay, wedge dash is mainly used for one, when you have one chiral center. Okay, when you have one chiral center, and there will be two normal stick line, which is this, and you're gonna use this wedge, bowl wedge, and also this dotted wedge shape. Okay, so the bowl wedge will be pointing towards the viewer, meaning sticking out. Okay, while the dotted wedge will be away from the viewer, meaning to the back of the structure. And for the Newman, okay, you can draw it in either staggered or eclipse conformation. Okay, so just draw the circle first and draw the front carbon, but with only 3 bonds. Okay, because the CC bond is not shown. You are viewing it directly from this side. Okay, from this side, and depends on whether it is staggered or eclipse. So you draw the back carbon, okay, accordingly. Okay, the atoms and group of atoms. And for the sawhorse, draw the straight line first, okay, before drawing all of the bonds, okay, at the carbon, the two chiral carbon, okay, then only whether it is eclipsed or staggered, you can start on drawing or putting the atoms or group of atoms at the back carbon. Okay, so if you notice, the carbon here is not shown, but sometimes it will be drawn as well. So it depends on the example use or reference that you see. Okay, sometimes it is shown the carbon, but most of the time it will be in this stick shape. Okay, where these two are the carbon or the chiral center. Okay, if there is no other question, then I want to continue with our lecture. Okay, last week we stopped at diastromas, right? So we stopped at diastromas. Oh, saya tak share ke? It suddenly stop. Share screen. Okay, so we have covered a few types of isomers. Okay, the first, which is the constitutional. Earlier, there are three types. Okay, let's do a little bit of recap first. Okay, we have the chain isomerism. So these isomers is where you have the same number of same chemical formula, but the way the carbon is arranged is either in a straight chain or it could be in branching. Okay, and for positional isomers, still in the same functional group. Let's say you have alcohol, but the position of the OH could be different. It could be on the first carbon, second carbon, third carbon. Okay, and while the functional isomerism, the functional isomerism is they have the same chemical formula, but the functional group is totally different. Okay, like you could have aldehyde and ketone sharing the same number of carbon, hydrogen, and oxygen, or you could have alcohol becoming the functional isomers of ether as well. Okay, so that is the constitutional isomers. And then for conformation is when you rotate the carbon-carbon single bond, okay, at 60 degrees. This can be easily shown using the um, Newman projection and also the Sawhorse projection. Okay. Uh, Now on to the stereo isomers. Okay, some few keywords that you have to know, which is the stereo isomerism. What is optically active? What is optically inactive? So what optically active is those compound that can rotate the plane polarized light. Okay, which is based on this light. So you have the light source and a polarizer giving out one plane of light, okay, the light wave, and whether your sample or the organic sample can rotate this light. Okay, it can rotate it to the right or to the left. If it's rotate to the right, to the right, then it will be dextrorotatory, or use the positive sign, or if it's rotate to the left, then you can use the negative sign, or L. Those compound that doesn't rotate the plane polarized light at all, that will be considered as optically inactive. Okay, optically inactive. Then you have to know how to differentiate, okay, between chiral and non-chiral or achiral molecules. So normally, those chiral molecule will have this chiral center, okay, or chiral carbon available in the compound. So this chiral center must have 4 different atoms or group of atoms attached to it. Okay, so if it contains, it fulfill this criteria, then that carbon would be considered as the chiral center. And once you have this chiral compound, okay, that chiral center will give you a chiral compound. You will end up having two optically active compound, and this compound would be called as a pair of enantiomer. Okay, like earlier, the rotation, okay, the compound can rotate to the left and to the right. So these two pair would be considered as an enantiomer. Okay, so it will be called as enantiomer. This one. So the enantiomer is the mirror image, okay, mirror image of each other, but it is non-superimposable, okay, meaning that you cannot overlap. So you can't overlap it. So this is how you can calculate the numbers of isomers based on the uh, how many chiral centers that it is that the compound has. So if it contains 2, for example, then there would be 4 isomers available. Okay, coming in from 2 pairs of enantiomer, you're going to end up with 2 pairs of enantiomer. Example that is shown here is using the tartaric acid. So what we have over here, we have D and L. So this would be considered as a pair of enantiomer because they are mirror image. So if I put a mirror over here, they are mirror image with each other, but you cannot superimpose them. Okay, you cannot take compound tartaric acid D, and then overlap it with L, tartaric acid. So that is not possible. And then, okay, this is the two chiral center. Okay, you cannot have a plane of symmetry inside the compound. But over here, we have this mesotartaric acid. So this mesotartaric acid is optically inactive. Okay, optically inactive. The reason is because it contains an internal plane of symmetry. So if I put like a mirror over here, so this side, okay, the one on the bottom is an exact mirror image of the one on top. So the uh, symmetry sort of internally compensated. So that's why it is not optically active. And this compound is considered as a meso compound. Okay, even though it contains the chiral center, okay, it is not optically active. And this one, which is diastereomer. So when you compare between 1 and 2, this would be considered as enantiomer. Enantiomer because it is mirror image but not superimposed. But if let's say you want to compare between compound 1 and compound 3, so compound 1 and compound 3 are not mirror image with each other, but at the same time it cannot be superimposed as well. So they are two different isomers, okay, different arrangement. So what do we call them? So these are considered as a diastereomers. Okay, so diastereomers, the simple definition would be you have a compound which is not mirror image with each other. So this compound 1 and compound 3 are not mirror image with each other, and they also cannot be superimposed. Okay, you cannot overlap them. So this is true for compound 1 and compound 3, and when you want to compare compound 2 and 3 as well, because these two are enantiomer. These two are already an enantiomer. Okay, but between 1, 2, and 3, okay, this would be called as a diastereomer. So the properties of diastereomer, totally different physical and chemical properties. So they have different melting point, boiling points, solubilities, even though uh, the name is still tartaric acid, okay, but they will have different properties altogether. Okay, even their reactivity, chemical reactivities also would be different than the normal tartaric acid. Okay, so that would be on diastereomers. Now on to the naming part, okay, which is nomenclature. So earlier in unit 2, you have learned on how to name organic compound. But now we want to include the stereochemistry to the naming as well. Okay, so basically, this is to specify the stereochemistry of each compound. But the nomenclature that we are going to see first is nomenclature for chiral centers. Okay, the nomenclature of the chiral centers, which is the carbon that is having 4 different uh, atoms or group of atoms attached to it. And the label that we are going to add to the name, okay, you have learned on the IUPAC nomenclature, that will be used the same way, okay, nothing will be different, but we just going to add these 2 letters, which is the R and S, okay. This R and S will be used as a prefix, okay, in front to denote the chirality of that compound. So based on this, to specify the 3D configuration of chiral center, you have to assign priorities of the 4 substituents. So earlier, you have your C in the middle, the carbon in the middle with 4 different group. I use numbers now. 1, okay, 2, 3, and 4. So these 4 different atoms or group of atoms must be arranged in a priority. Okay, there must be a priority in which one will be number 1, which one will be number 2, number 3, and number 4. Because based on this, it is how you are going to determine whether it is R or S. Okay, once you determine the priority of the 4 substituents to this carbon, okay, the chiral carbon, the lowest priority, okay, substituents will be put at the back. Okay, will be put at the back. Okay, according to the priority of the substituents, okay, the lowest that you can have, okay, will always be hydrogen. Okay, lowest is hydrogen. Let's say you have carbon, okay, hydrogen, and this could be CH3, OH, and Br, for example, bromine. So among these, okay, we always try to determine which is the lowest, okay, lowest priority. So if you see any hydrogen that is available, so this would be considered as the lowest priority. Okay, later we will see why. So we place the lowest priority at the back of the flying wedge, okay, with compounds having 1 chiral carbon, or vertical with compounds having 2 or more chiral carbon in a Fischer projection. Then only you determine whether it is clockwise or anti-clockwise sequence for the 3 other substituents. Okay, if the position of the 3 other substituents increase in priority from left to right or clockwise, that will be considered R. Okay, rotate this way, or if it's rotate this way, it will be considered S. So here on the flying wedge, okay, the lowest priority will be put at the back. So how you draw a flying wedge earlier? So you have carbon and with two uh, line here, okay, and then you have this bowl wedge. Okay, the bowl wedge and also the dotted wedge. So by having the word here, the lowest priority to the back of the flying wedge, which is this one, or the wedge dash, the lowest priority is this one, okay, which is to the back. So whatever it is that substituents that you have having lowest priority, let's say hydrogen, so you always put it on the wedge dash, uh, sorry, the dotted dash position, the dotted wedge, which is this one. Okay, so if it is in the where is it, fissure, okay, or any other projection, you can place it here. It is said to be in vertical, so the one that is pointing on top. Let's say you have the Newman projection, okay, so you can place the hydrogen here, or if you use the sawhorse projection, you can put the hydrogen on top, probably. Okay, so now once you put the hydrogen at the back, based on the other three substituents, okay, maybe substituent 1, 2, and 3, you will determine, okay, according to the order of priority, whether it rotate to the right or rotate to the left. Rotate to the right will be R, rotate to the left will be S. So the stereocenters would be labeled as either R or S. So what is the stereocenters? The carbon. Okay, the carbon would be labeled either R or S. So this naming, okay, is based on the Kahn-Ingold system. Okay, so this R.S. Kahn and also C. Ingold and also V. Prelog, who are the one who developed this R and S naming system. So the four substituents around the chiral carbon must be first ranked in order of decreasing priority. So let's say we have A, highest priority, B, second highest, C, third highest, and you have the lowest priority D. So always put the lowest priority at the back, which is this one. And we will try to see the carbon, okay, the carbon at this angle. If you look at the eyes, okay, this is your eyes, okay, we will see it from the front, okay, and this is how you are going to determine whether it is rotate to the left or to the right. And based on this, okay, if you look on this structure, the D is not visible anymore because we are viewing it from in front. Okay, the D no longer visible. So that's why we only refer to the A, B, C, which is the highest, second, and third highest priority. So if you have A, B, and C, okay, and it rotate to the right, to the left like this, okay, anti-clockwise, it will be considered as S, okay, and take note that the A doesn't have to be always on top, okay, that means that you can have carbon, you can have A over here, B and C, okay, still it will rotate anti-clockwise, this will be still S, okay, even if you change the position, let's say you have C, okay, and then you have A, B, and C. Okay, this will still be rotate anti-clockwise S. Okay, so this side is when you have an R configuration whereby the position of the highest, second, third highest priority is clockwise. Okay, so you have A, B, and C. So this would be R. So A, B, and C, that would be the R configuration. So the R, A, and S. So R has the name rectus. S is for sinister. This is a Latin word. So the R and S, okay, will be added as prefix to the chiral compound. For example, it will be written something like this: R2-bromobutane. So the R and S will be written in bracket, and it will be placed first. Okay, you have to write it first, whether it is an R or S, then dash followed with whatever the original name is without the stereochemistry. Okay, let's say it is bromobutane, 2-bromobutane, so you just write 2-bromobutane. So once uh, you see this kind of a structure, okay, a person would know that the structure is 2-bromobutane, but once you include the R and S, people will know that, oh, this compound contain a chiral center, and the position of the atoms surrounding the chiral center is clockwise. Okay, is clockwise, meaning rotate to this side. And from here, you can actually draw back the structure according to the stereochemistry. So if known, the sign of rotation of plane polarized light may also be added. Okay, so you can also include whether it rotates to the right or to the left as well. Like the negative is L, positive is D. So R in bracket R, and then the rotation, okay, and followed by the usual name. Okay, but this sign can only be determined by doing the plane polarized light test. Okay, so you cannot determine according just on the structure. Okay, sometimes these values may not be the same like in theory. Okay, so now we will see on the rules of assigning priorities to the substituent. So you have A, B, C, and D. Okay, D being the least, okay, which I've told you earlier. If you see a hydrogen on the compound, on the chiral center, that will definitely go to being the having the least priority. So the first rule would be look first at the atoms directly attached to the stereocenter. Okay, you have to identify the four atoms. Okay, four atoms directly attached. Then, okay, precedent is in the order of highest atomic number. So you have to select the atom with the highest atomic number. Okay, highest atomic number. Let's see here, for example, you have carbon with hydrogen, and then iodine, bromine, and also here you have CH3. But read the word carefully. Look at the atoms, okay, directly attached to the stereocenter. So if you have a CH3 like this, you don't look at the whole group, which is the CH3. Okay, you only look at the carbon. Okay, we only see the atomic number or the molecular weight of the carbon itself. So hydrogen, the atomic number would be 1. Okay, here already written. Iodine is 53, bromine is 35, and carbon is 6. So according to this, hydrogen will be considered as D. Okay, D, uh, because the number is just 1. Okay, and then you go back to the iodine, bromine, and carbon. So among these, iodine would be considered to be having the highest priority because the atomic number is 53, while bromine would be second or B, the atomic number is 35, and carbon here would be considered as the third highest priority. Okay, having 6 atomic number. The atomic number is 6. So now the way you are going to view it is always put the lowest priority at the back. So the hydrogen, in this case, it is hydrogen. It will be put at the back, and you are just going to focus on the A, B, and C. Okay, which is in this example, you have your CH3, you have your iodine, you have your bromine. So according to this, it is said that the configuration is R, meaning clockwise. So is it true? If you look here, okay, it will be rotate this way. Okay, if you still cannot, you feel like it is hard to visualize when it is at angle like this, then you can convert it into C, having CH3, CH3, and then your iodine and bromine here. So according to this, iodine will be A, bromine is B, your carbon here would be C, carbon that is on the metal. So it will rotate this way, which is clockwise, hence R, okay, in terms of the configuration. And the name here will follow the usual naming system. Okay, usual naming system. Now, rule number 2. If two atoms are of the same precedence using rule number 1, then you proceed along the two respective substituents chains until you reach a point of difference. So what it means over here, let's see. Uh, for example, we have here carbon, all hydrogen, having hydrogen, 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 all is the same. Okay, but what if, let's say, uh, I give another example. So you have C, okay, CH3. This one is CH2, CH3. Okay, this one, let's say hydrogen and Br. So according to the first rule, we know that hydrogen will be D. Okay, the atomic number is 1. And bromine would be A. The atomic number is 35. But between these two, the atom that is directly bonded to the chiral carbon or the chiral center is carbon as well, C and C. And these two C have the same atomic number, which is 6. So which of these two you are going to select as B, okay, which is having the second highest priority. So once you find a situation like this, okay, proceed along the two respective substituents chain until you reach a point of difference. That means once you reach the same like this, C, you proceed this way and see where does the difference occur. That means, okay, you have your CH3, okay, H, sorry, H, H, and then another one is C, H, CH3. Okay, so this is connected or bonded to the chiral center. This one also bonded to the chiral center. So the carbon just now is the same, okay, which is this one. But then you check whatever atoms that is bonded to that carbon. Hydrogen, on this side, you have hydrogen as well. And second hydrogen, still the same. Okay, because here you have to proceed until you reach a point of difference. Then here on this ethyl group you have carbon, but on this methyl it is hydrogen. So among carbon and hydrogen, this will have higher priority because the atomic number is 6 and this is 1. So based on this argument, okay, this would have to be selected as B. Okay, B, while this one would be C. Okay, so once you reach this situation where the atom that is directly bonded to the chiral center having the same number of atomic number, okay, having same priority, so you proceed along the line, okay, to see the first points of difference. Okay, once you select that, so you have your B, C, and A, you can actually determine the R and S configuration. So let's take a look at this example. So here it is already written. It is R2-iodobutane. What we have to do is to verify whether the configuration is correct or not. Okay, whether it is truly R or S. So based on this, the D has already been given, which is this one. So the hydrogen will be placed at the back, and you are going to view it from this side. Okay, you are going to view it from this side. If you cannot visualize it this way, you can draw back. Feel free to draw back. So carbon, iodine, CH2, CH3, and then your CH3. So you have A, B, and C. So A, B, and C, where it should be, the rotation should be, whether it is clockwise or anti-clockwise. Clockwise ke anti-clockwise? A, B, and C. Anybody? Dia akan rotate clockwise atau anti-clockwise? Syazah? Dia akan rotate ke mana? A, B, C. Hello? Tak ada orang ke?
Sir,
Ya? Yeah.
macam mana nak bayangkan?
Macam mana nak bayangkan? That visualize tu, sebab tu saya cakap, you dah buka tak software yang, dah try guna tak software yang saya suruh cuba minggu lepas? Dah cuba tak? That software actually will help you to try and visualize better in your head. There's no other way besides yang itu one of the tools lah. Because back in the days, tak ada pun software-software tu. Kita sendiri yang kena bayangkan macam mana structure tu terbentuk. And another way would be to use 3D models. But 3D models ada dekat lab je. So, unless you have your own 3D models at home. So, I know this would be, how to say, susah sikit lah. Tapi, the easiest would be try to go and see the 3D structure using the ada banyak software lah yang last week tu saya tunjuk just one example. So based on that, you have try to imprint that in your head, because in the carbon, okay, carbon punya geometry will always be tetrahedral. Okay, it will be tetrahedral for sp3. Okay, sp3 it will always be tetrahedral unless it is double bond. Itu lain cerita. But once it is in this shape, okay, the hydrogen will be placed at the back. Tadi mata tadi mana? Gambar mata. This one. You are viewing it from here, directly looking at the carbon center. This will translate to this structure. Okay, kenapa saya cakap tadi hydrogen kat sini dah tak ada. Kenapa tak ada? Because you are viewing it from this angle, directly on the carbon. Okay, hydrogen tu dekat belakang carbon, at the back. Okay, it could be hydrogen or it could be any other group, but the thing is it is the least priority lah, priority paling rendah. So based on that, kita just focus on group A, B and C. Okay, so if it is rotate to the right, then that will be considered as R. If it is rotate to the left, that will be S. So based on this, I have convert this 3D structure, okay, using the flying wedge or the wedge dash projection into the 2D shape. Let me draw this again. Okay, you have C, and then with iodine on top, and your CH3 and this CH2, CH3. Okay, the priority has also been given. This would be A, but if you want to determine, iodine will have higher priority because this is having higher atomic number compared to carbon and carbon. And between these two carbon, they are the same, but using rule number 2, which is this one, okay, the first point of difference is same hydrogen, hydrogen, but it has another carbon. So this would be B and this is C. So my question now is whether it rotates to the right or to the left. Once you determine whether it's rotate to the right, to the left, then it will be converted into R or S configuration. So based on this, you have A, B, and C. The rotation will occur this way. So clockwise would be R. Okay, would be R, and then this is correct. Then for this second structure, this is this one. Okay, the priority list has already been given. This is A, B, and C. Hydrogen is D. So this will be at the back. Okay, you can convert this into something easier to see, which is draw the carbon with just 3 bonds. Okay, draw the carbon with just 3 bonds. So you have your CH3 on top. This would be your A, and then another CH2, CH3, the green colored one. Okay, this would be C, and then your CH3 2. So this would be B. So based on this, you have to determine the rotation as well. So the rotation must go from A, B, C. So you have A, B, and C. So this is anti-clockwise. So when you have anti-clockwise, the configuration would be S. It would be S. So this is until rule number 2. Okay. Now on to rule 3. Okay, rule 3. So here, if there is any double or triple bonds, okay, that is attached to the chiral center, is the chiral carbon. Let's say you have carbon like this, okay, this carbon, and it is attached to a C double bond C, or like for example this one, C double bond O. So this would be treated this way, okay. This one you have to remember. There's no other way besides. C double bond C will be treated as this. C triple bond C will be treated as CC or with all of the carbon. Okay, C double bond OH, which is aldehyde, will be treated as C with O and then OC, while C double bond OH, carboxylic acid, will be this way. Okay, after you convert this structure into this, then only you see you go back to rule number 1 and rule number 2. If they have the same what you call that atoms that attach to the first carbon, okay, try to look for the uh, point of difference. Okay, you proceed along the way and see the first point of difference. Okay, this one, let's try. So assign R and S configuration for the following. So based on this, if you see any hydrogen that is available on the structure itself, okay, so this will be considered as having the least priority. So H will be D, this one D, D, and D, D as well. Okay, so once you establish that, you will have to determine the one with highest priority. Okay, uh, the first structure, which is this one, so you have Cl, and then another Cl, and then CH2Cl. So Cl and Cl, these two are having the same atomic number. So this is same atomic number. What about this carbon? So this would be C among Cl and carbon, chlorine and carbon. Chlorine has higher priority. So this carbon would be considered C. But then again, is this carbon a chiral center or not? Chiral carbon must be bonded to 4 different atoms or group of atoms. But in this case, you have 2 chlorine. So for the first compound, you cannot assign R or S. Okay? Because this is not chiral center. You have 2 chlorine over there. Then for the second one, okay, identify the atoms that is attached to the carbon. You have C, C, and Br. So from this, Br will have higher priority. So this will be A according to the atomic number. And then between these two carbon, okay, so if you look, CH2, CH2, the same. Then you have to proceed along the way to see the first point of difference. So the first point of difference here is between chlorine and also oxygen. So between these two, chlorine will have higher priority because it have the atomic number of 35.5, while for oxygen is 16. Okay, so this would be B and this would be C. Okay, after you have determined this, then only you can determine whether it is an R or S configuration. So if you cannot visualize it this way, okay, I have always advise you to convert it into a more 2D shape by omitting the hydrogen or the D group. So you draw C with your Br, okay, and then CH2OH, and then CH2Cl. You have your A, you have C here, and this is B. Then determine whether this rotate to the left or to the right according to the ABC lah. So A, B, C. So this one rotate anti-clockwise. So anti-clockwise, this would be labeled as S. Okay, as S. So that is how you assign the configuration. So for this one, and this one, uh, you try to see whether uh, you can get the same answer, okay, as that is I already placed the solution over here, okay, but after this when you go back, try to look and see whether you can actually get the same configuration which is given as in the answer over here. Okay, so you have S, which is the same like this. Okay, if you have done this numerous times, okay, uh, eventually you don't need to convert into this kind of structure anymore. Okay, you can try to see whether based on this structure alone, something like this, you can actually try to visualize whether the A, B, and C, because this is pointing in front towards you. Okay, and this is C. This uh, dotted wedge. This is pointing away from you, and you always try to put your eyes from this side. Okay, your eyes, you cannot view it directly from here. Okay, which is like how you are looking at the screen right now. Okay, you have to try and visualize your eyes to be at this side. Okay, this so horse. Okay, so I think I'm just gonna stop until this part first. Okay, and let you go back after this and try to look more into this. Okay, all of this, whether you can obtain the same answer or not. And next class we will start with the sawhorse and the rest of the projection. Okay, using all of this R and S configuration, because if you do not master this or understand this, because this is just one chiral center. Okay, in sawhorse later there would be two chiral center. You have to determine this one and also this one. You have to determine the configuration R and S. Okay, and this would be easier because the uh, lowest priority group can always be put at the back, but using a sawhorse projection, okay, the H is here. Okay, so it will take how to say, a harder effort, okay, in order to visualize whether it is R or S. Okay, so try to go back and understand this part first. Okay, and we will continue with the Sohos projection this Friday. Class bila? This Friday. Our class will be this Friday. It will be, yeah, Friday. Okay. So any question? Ada soalan lain? Beside how to visualize. That one I cannot help you. So I hope you go back and try to see any of the uh, 3D chemical software. Okay, so that is one way how to make yourself familiar on the arrangement of this atom, okay, in space, because I cannot show you the exact 3D models that I have, because 3D models tu ada dekat lab. See? Saya tak boleh bawa balik rumah. But then again, the 3D software is one of the most useful tools that you can have. It's free. Kalau tak ada dekat computer, if you have your tablet, you can see my ni, right? I'm using where is it? I'm using this one. This one also is free, molecular orbital, in which you can select, let's see, carbon, and you can have another carbon. Let's see, you want to create hydrogen, okay, or another tools would be this one, WebMO, also free. Nope. Okay, so you can draw, select carbon. This would be carbon, and then you can add the hydrogen, hydrogen. Okay, and then okay, all of this structure. Once you draw, you have to how to say, correct the orientation, because if it is like this, okay, this is not the correct geometry. So what you do, for example, if you use this WebMO, you just press clean up, then select geometry. So this would be the correct geometry. So like this, for example, this is staggered conformation. So you see you have carbon and carbon, okay, hydrogen, but in staggered. So this is Newman projection. This is Sawhorse. Okay, you are viewing it at a slight angle. But what if there is only one carbon? Let's see. Okay, you have one carbon, and probably I have one oxygen. Sorry. Okay, this could be another hydrogen, another CH3, and this could be an amine. So I press clean up geometry. So this carbon in the middle, okay, this one, the one that sorry, okay, the carbon that is in the middle, the black color, is the chiral center, whereby you have the red one is your OH, the blue color would be your amino group, and this other CH3 would be your uh, methyl, okay, another substituent. So how you are going to view it or visualize, okay, this white, okay, the one okay, this white would be your hydrogen, and the hydrogen will always be put at the back, and you are viewing it like this. So sekarang you tak nampak hydrogen lagi. So from this, you can determine which one is having higher priority, and also the orientation, whether it is clockwise or not. So let's see here, for example, kat sini saya tak boleh tulis, but uh, let's just assume the red color will be your oxygen, and the blue color is your nitrogen. The other black one is carbon. So based on these three, okay, you have to compare the atomic number of the atom that is attached to the chiral center. So oxygen will be the highest, having 16, okay, followed by nitrogen. Then carbon would be 6. So oxygen would be A, red A, blue B, and the black one would be C. So based on this structure, okay, it will be rotate anti-clockwise. Okay, anti-clockwise. So the orientation will be S. Okay, the orientation will be S. But what if I change the position? I change the position. This one is now carbon. This would be your hydrogen. Okay. So the position of the carbon and nitrogen is already changed. So the priority is still the same. O, oxygen, nitrogen, and then carbon. But now, instead of rotating anti-clockwise, it is now rotating clockwise. So the what do you call, the orientation now would be R. Okay, but they are still the exact same compound. I did not change the number of carbon or hydrogen, just the position of the carbon and nitrogen. Okay, the carbon, nitrogen, oxygen are all having the same number. So you can use this as well. This one I think is also available in phone. Okay, in your phone, quite useful. Another, you can also use this. Oh, this one cannot. This is for protein. Wait. WebMO. This one. Okay, but this is we haven't reached into this topic yet. So this is actually later for cyclohexane. Okay, whereby it is in the shape of chair conformation and also boat. So later, once we have covered that, you can also try this app as well. Okay, I'm not sure whether it is available in uh, what do you call that, Android or not, but try to look, okay. But my suggestion would be the WebMO, this one. This is my personal preference to use. Okay, so any question? Ada soalan? Anybody?